A-Level Mechanics, Simple Harmonic Motion, Part 2. Let's see a few more results that we can obtain from the simple harmonic motion equation. So far we've derived the following equations for any object moving in simple harmonic motion. We've had d2x by dt squared is equal to minus omega squared x. That's the equation from which all the other results are derived. We've had v squared equals omega squared into a squared minus x squared. We've had x equals a sine omega t plus epsilon, where t, the time period, is 2 pi over omega, and we know the frequency nu is equal to 1 over t. Looking at equation 1, we can see the acceleration of an object is always towards a fixed point and is proportional to the distance from that point. And as I say, all the other equations are derived from it. Now equation 2, v squared equals omega squared into a squared minus x squared, enables us to calculate the velocity v of the particle when we know its position x. However, we may want to know the velocity at any given time. Now we've got x is equal to a sine omega t plus epsilon, and we can differentiate that. That gives us dx by dt is equal to a omega cos omega t plus epsilon. But dx by dt is v, so we've got v equals a omega cos omega t plus epsilon. This is a new equation that gives us the velocity at any given time. Let's look at an example. A particle moves according to the equation x equals a sine omega t. It performs 8 cycles per second and after coming to rest travels 1.4 meters before coming to rest again. In part 1 we're asked to find the amplitude of the oscillations. Now the object comes to rest on either side of the equilibrium position. So the equilibrium position is equidistant from 2 consecutive rest points. So the distance between 2 consecutive rest points is twice the amplitude. We can see this in a diagram. The rest positions are at the top and at the bottom of the motion. The equilibrium position is halfway between them. Now the distance between the rest positions is 1.4 meters. So the amplitude is a half of 1.4, which is 0.7 meters, and so we have as a result the amplitude is 0.7 meters. Now in part 2 we're asked to find an equation for its velocity at time t. Now we're told the particle performs 8 cycles per second. So the frequency nu is equal to 8. That means t is equal to 1 over 8, and omega, which is 2 pi over t, is equal to 2 pi divided by 1 over 8, which is 16 pi. So the equation for x becomes x equals 0.7 sine 16 pi t. Now if we differentiate, v is dx by dt, and that's equal to 0.7 times 16 pi cosine 16 pi t. So the equation for the velocity is v equals 11.2 pi cosine 16 pi t. Now in part 3 we're asked to find its position and velocity after 0.02 seconds. Well, to find its position we can substitute t as 0.02 seconds in the equation x equals a sine omega t plus epsilon. So we have x is equal to 0.7 sine 16 pi times 0.02, which works out to be 0.5910 meters. And to find the velocity, we can use v equals a omega cos omega t plus epsilon. So that gives us 0.7 times 16 pi cosine 16 pi times 0.02, and that works out to be 18.8535. So we have the displacement is 0.591 meters, and the velocity v is equal to 18.9 meters per second. Let's have a look at some alternative forms of the distance-time equation. Now we know the differential equation d2x by dt squared equals minus omega squared x has a solution x equals a sine omega t plus epsilon. However, the solution can be written in other forms. For example, it can be written as x equals a cosine omega t plus epsilon, or x equals a sine omega t plus b cos omega t, where the amplitude a squared is equal to a squared plus b squared, and epsilon is the inverse tangent of b over a. Now we can see why this is. In equation 2 we've got x equals a cos omega t plus epsilon. But we know cosine of theta is equal to sine of theta plus pi by 2. So a cosine omega t plus epsilon is equal to a sine omega t plus epsilon plus pi by 2. And so we see equations 1 and 2 only vary by having a different value of the arbitrary constant. To see why equations 1 and 3 are the same, we need to use the compound angle formula. The sine of alpha plus beta is equal to the sine of alpha cos beta plus cos alpha sine beta. We have a sine omega t plus epsilon is equal to a sine omega t cos epsilon plus a cos omega t sine epsilon. And this can be rearranged as a cosine epsilon sine omega t plus a sine epsilon cos omega t. If we let capital A equal a cosine epsilon and capital B equal a sine epsilon, then we have a sine omega t plus epsilon is equal to a sine omega t plus b cos omega t. So we have capital A squared plus capital B squared is equal to the amplitude squared, that's little a squared, into cos squared epsilon plus sine squared epsilon. Now, cos squared epsilon plus sine squared epsilon is equal to 1. And so that's equal to a squared, the amplitude squared. And we have capital B over capital A is equal to a sine epsilon over a cos epsilon. The a's cancel and leave tan epsilon. So epsilon is equal to the inverse tangent of b over a. And this shows the equations 1 and 3 are equivalent. So we have 3 forms of the equation that give x in terms of t. Now it's worth noting, if the motion starts at x equals 0, that means it starts at the equilibrium position, then equation 1 is the best form, because epsilon becomes 0, and so we can write the equation as x equals a sine omega t. If the motion starts at x equals a, that means it starts at the positive maximum extension, then equation 2 is the best form, because again epsilon becomes 0, and so we can write the equation as x equals a cos omega t. Let's look at an example. Example 2. Imagine a block resting on a smooth horizontal surface and is attached to a spring which is also fixed to a wall. If the block is given an impulse, it would start oscillating from the equilibrium position. We could use the equation x equals a sine omega t. If the block was pulled back and then released, it would start oscillating from the maximum displacement. We could use the equation x equals a cos omega t. Example 3. A particle moves satisfying the equation d2x by dt squared is equal to minus 49x. When t is 0, x is equal to 6 meters and v is equal to 28 meters per second. In part 1 we're asked to find x in terms of t. Well, to solve this we have omega squared is 49, and so omega is equal to 7. Now let x equal a sine 7t plus b cos 7t. When t is 0, then x is 6. So 6 is equal to a sine 0 plus b cos 0. Well, sine 0 is 0 and cos 0 is 1. So 6 is equal to b, or b equals 6. So if we differentiate a sine 7t plus b cos 7t, we get 7a cos 7t minus 7b sine 7t. So if t is equal to 0, then v is equal to 28. So 28 equals 7a cos 0 minus 7b sine 0. And again, cos 0 is 1 and sine 0 is 0. And so we have 28 is equal to 7a, or a is equal to 4. And so our answer is x is equal to 4 sine 7t plus 6 cos 7t. Now, in part 2, we're asked to find x and v when t is equal to 1.2 seconds. So if we've got x is equal to 4 sine 7t plus 6 cos 7t, when t is equal to 1.2, x is equal to 4 sine 7 times 1.2 plus 6 cos 7 times 1.2. Remember to have your calculator in radians, and it works out x is equal to 0.30266. Now we've got dx by dt, which is our velocity v, is equal to 7 times 4 cos 7t minus 7 times 6 sine 7t. So if t is equal to 1.2, we can substitute that into the equation. V equals 28 cos 8.4 minus 42 sine 8.4, which works out to be minus 50.433. And so our answer is x is equal to 0.303 metres and v is equal to minus 50.4 metres per second. Now in part 3 we're asked to find the amplitude of the motion. Well, the amplitude is equal to the square root of a squared plus b squared, which is equal to the square root of 4 squared plus 6 squared, or the square root of 52, which is 7.211. And so the amplitude is 7.21 metres. And then finally in part 4, we're asked to put the equation in the form x equals a sine omega t plus epsilon. Well, if we start with x equals a sine omega t plus epsilon, we've got x is equal to a sine 7t cos epsilon plus a cos 7t sine epsilon. But x is equal to 4 sine 7t plus 6 cos 7t, and so a cos epsilon is 4 and a sine epsilon is 6. So a sine epsilon over a cos epsilon is 6 over 4, or tangent of epsilon is 1.5, which means epsilon is 0.9827 radians. Now we already know that the value of a is 7.211. So our answer is x is equal to 7.21 sine 7x plus 0.983. Now if we want to, we could draw the graph of x equals 4 sine 7t plus 6 cos 7t, and we can see on the graph that we've actually got an amplitude of 7.21. Let's have a look at one more example. Example 4. A light elastic rope of natural length 1.5 meters has a mass of 2 kilograms attached to one end and is suspended from the other end at O. The modulus of elasticity is 147 newtons. In part 1, we're asked to show that the extension in the rope is 0.2 meters. Well, to solve this, let the extension in the rope be E. Now we need to draw a diagram and mark in the forces. There is the weight of the object, 2g, which is acting vertically down. There's also a tension in the rope T, which is acting vertically up. So if we resolve vertically, we have T is equal to 2g, which means T is equal to 2 times 9.8, or 19.6 newtons. If we now use Hooke's law, which is T equals lambda x over L, we've got T is 19.6, lambda is 147, and the natural length is 1.5. So 19.6 equals 147e over 1.5, or we can work out e is equal to 19.6 times 1.5 all over 147, which is 0.2, and so the extension is 0.2 metres. We're now told the mass is then pulled down to a distance of 2 metres below O, and then released. In part 2 we're asked, derive an equation giving its distance below the equilibrium position in terms of t. Well, let the extension below the equilibrium position be x. Again, we need to draw a diagram and mark in the forces and the acceleration. Because the extension is down, we'll take down as the positive direction. So we have the weight of the object, 2g, acting vertically down. We have the tension, which we can now call T, and that's acting vertically up. And we have an acceleration, we can label it A, and that will be acting vertically down. So resolving vertically using F equals ma, we have 2g minus t equals 2 times the acceleration A, or 2 times d2x over dt squared. Using Hooke's law, we've got t equals lambda x over L. And again, we have the elasticity is 147, the natural length is 1.5, but the extension is 0.2 plus x. And so we have t is equal to 147 times 0.2 plus x all over 1.5. And that works out t is equal to 19.6 plus 98x. Now if we substitute that value of t into equation 1, we get 2 times 9.8 minus 19.6 plus 98x equals 2 times d2x by dt squared. In other words, 2 times d2x by dt squared is equal to 19.6 minus 19.6 minus 98x. So d2x by dt squared is equal to minus 49x. And that is our standard equation for simple harmonic motion. And it tells us omega squared is equal to 49, and so omega is equal to 7. Now the motion starts at maximum extension of 0.3 meters, so we can use the equation x equals a cos omega t to get x is equal to 0.3 cosine 7t. Now in part 3 we're asked to find the time when the string first goes slack. Now the equilibrium position is 0.2 meters below the natural length, and the string will go slack when the mass reaches the natural length. In other words, x is equal to minus 0.2. So 0.3 cos 7t is equal to minus 0.2. So cos 7t is equal to minus 0.2 over 0.3, or 7t is equal to the inverse cosine of minus 2/3. That tells us t is equal to 1/7 times the inverse cosine of minus 2/3, and that works out to be 0.3286. And so the rope goes slack after 0.33 seconds.